Have you ever wondered what powers our most ambitious space missions, or how some medical devices can operate inside the human body for years without a recharge? The answer to that question lies in a tiny, yet incredibly powerful technology called nuclear batteries. These are not your run-of-the-mill batteries. Instead of relying on chemical reactions, nuclear batteries harness energy from the decay of radioactive isotopes. This makes them incredibly stable and reliable. They're the unsung heroes behind many of our technological marvels. From spacecraft exploring the farthest reaches of our solar system to pacemakers that keep hearts beating, nuclear batteries deliver dependable, long-term power where it's needed most. As our technological capabilities continue to expand, so too does the demand for energy sources that can keep up. Today, we're diving into the world of nuclear batteries, the long-lasting powerhouses that could revolutionize energy as we know it. So, what exactly are nuclear batteries and how do they work? To unravel this question, let's take a deep dive into the atomic world. Nuclear batteries, also known as atomic batteries or radioisotope generators, are unique power sources that tap into the energy released by decaying radioactive isotopes. Now, if you're wondering whether this has anything to do with nuclear reactors, well, you're not entirely off track, but there's a key difference. While nuclear reactors also rely on radioactive decay, they use a chain reaction to generate power. This can lead to a runaway reaction if not properly controlled, which is why we see safety concerns with nuclear power plants. On the other hand, nuclear batteries don't rely on a chain reaction. Instead, they use the steady, predictable decay of specific isotopes to generate electricity. This makes them incredibly stable and reliable. Now, the working principle of a nuclear battery is quite fascinating. As the isotope decays, it emits radiation, typically in the form of alpha or beta particles. These particles carry kinetic energy, which can be converted into electrical energy. Here's where the magic happens. When these charged particles collide with a semiconductor material in the battery, they excite the electrons in the material, causing them to move and create an electric current. And voila, we have electricity. The real beauty of nuclear batteries lies in their longevity. Because the radioactive isotopes used in nuclear batteries decay very slowly, these batteries can continue to produce power for years, even decades, without any maintenance. This makes them perfect for applications where changing a battery is either impossible or highly inconvenient, such as in spacecraft or deep-sea exploration vehicles. So, to sum it up, nuclear batteries are power sources that harness energy from the decay of radioactive isotopes to generate electricity, making them incredibly stable and reliable. With their long lifespan and ability to operate in extreme conditions, nuclear batteries are truly a power solution for the future. Nuclear batteries come in two main flavors: thermal converters and non-thermal converters. Each type has its own unique way of converting nuclear energy into electricity, and they're used in different applications, from space exploration to medical devices. First, let's talk about thermal converters. These devices generate power by converting the heat produced by radioactive decay into electricity. The process is fascinating. The radioactive material generates heat as it decays, and this heat is then captured and converted into electrical energy. One of the most commonly known thermal converters is the radioisotope thermoelectric generator, or RTG for short. RTGs have been a critical component in many space missions. They're like the Energizer Bunny of space exploration, continuing to provide power long after other energy sources would have run out. That's why they've been used in missions to places like Mars, where solar power isn't a reliable option. The Voyager spacecraft, which are still sending back data over 40 years after their launch, are powered by RTGs. Now, onto non-thermal converters, which work a bit differently. Instead of using the heat from radioactive decay, these devices directly convert the energy of radioactive emissions into electricity. One example of this is the beta-voltaic cell. Beta-voltaic cells are like little powerhouses. They're small, but they pack a punch. And because they don't rely on heat, they can be used in a wider range of applications, including small electronic devices. For instance, some pacemakers use beta-voltaic cells to ensure a steady, reliable power source that can last for years without needing to be replaced. So, whether it's powering a spacecraft on a journey to the farthest reaches of our solar system or keeping a life-saving medical device running smoothly, nuclear batteries play a critical role. They're like the superheroes of the energy world, quietly working in the background to keep our most important devices powered up. Non-thermal converters, such as beta-voltaic cells, directly harness energy from emitted radiation before it turns into heat, making them suitable for smaller applications. You might be wondering, how efficient are these nuclear batteries? Well, let's dive into that. Efficiency in the context of energy is about how well a system can convert one form of energy into another. In the case of nuclear batteries, it's about turning nuclear energy into electrical energy. Now, if we talk about numbers, nuclear batteries aren't the most efficient energy sources on the block. Their efficiency ranges from a mere 0.1% to around 8%. That might not seem like much, especially when compared to more conventional energy sources like solar or wind power, which can reach efficiencies up to 20 or even 30%. But before you write off nuclear batteries, let's talk about another crucial factor: energy density. Energy density is the amount of energy stored in a given system or region of space per unit volume. And this is where nuclear batteries really shine. They have an incredibly high energy density, which means they can store a lot of energy in a small space. This high energy density, combined with the stable and continuous decay of radioactive isotopes, gives nuclear batteries their extraordinary longevity. While a conventional battery might last for a couple of years, a nuclear battery can keep going for decades, even centuries. That's right, centuries. So, while they might not win any awards for efficiency, nuclear batteries pack a serious punch when it comes to longevity and energy density. These are the qualities that make them perfect for applications where longevity is key. Think about spacecraft voyaging into the far reaches of our solar system, or pacemakers that need to function reliably for many years. In conclusion, nuclear batteries might not be the most efficient energy source out there, but when it comes to longevity and energy density, they're in a league of their own. Their longevity and high energy density make them invaluable for powering devices that need to run autonomously for years, even decades. The potential of nuclear batteries goes beyond deep space missions and medical devices. Picture this: a future where the power outages and grid failures we've come to know are no more than a distant memory. A future where the energy that powers our world is not only sustainable, but also enduring. That's the promise nuclear batteries hold for us. You see, the energy sector is in a constant state of evolution, always searching for the next game changer. And nuclear batteries, with their impressive longevity and high energy density, could very well be it. They're like the Energizer Bunny of the energy world, continually going and going. These powerhouses don't just last long, they're incredibly stable, making them perfect for applications where reliability is paramount. Imagine a world where remote monitoring stations, emergency communication systems, and even your electric car never run out of juice. But their potential doesn't stop there. The sustainability aspect of nuclear batteries is equally exciting. They don't contribute to greenhouse gas emissions, and they require less raw material than traditional batteries. And while managing radioactive waste is a challenge, advancements in technology and recycling methods are helping to address this issue. So what does this mean for us? It means a future where our dependence on fossil fuels could significantly diminish. A future where our energy sources are not only robust and reliable, but also kind to our planet. That's the world nuclear batteries could help create. However, like all technologies, nuclear batteries have their hurdles. They're not as efficient as we'd like them to be, and their production involves handling hazardous materials. But remember, every revolutionary technology faces initial challenges. And as we've seen time and time again, our innovative spirit finds a way to overcome them. The potential of nuclear batteries goes beyond powering our devices. It extends to transforming our energy landscape. As we push the boundaries of technology, these tiny titans of energy stand ready to light our way. So there you have it, the incredible world of nuclear batteries. We've journeyed through the energy enigma, unpacked the mechanics of these atomic powerhouses, and explored the different types. We've seen how their efficiency might not be top-notch now, but their longevity and high energy density make them an invaluable energy source. And we've peeked into a future where these tiny titans could revolutionize the way we power our devices, from spacecraft to pacemakers. Isn't it fascinating how something so small can hold so much power? It's a testament to human ingenuity and our relentless pursuit of innovation. But our exploration doesn't stop here. There's a universe of technological marvels waiting to be unveiled. So if you're as captivated by this as we are, why not come along for the ride? Hit the like button, subscribe, and join us as we uncover more technological marvels. Until next time, stay curious and energized.